The outer solar system frame is quiet and structured, defined by gravity acting across long distances and long times. The Sun dominates the gravitational field, and the planets add smaller but important perturbations. In this wide region, trajectories are not guessed. They are computed from repeated measurements and from the known masses and positions of the solar system bodies. Most objects hold to these computations with ordinary precision. Their apparent paths may look irregular in the first nights after discovery, but as more positions are collected, the fitted trajectory becomes stable and the future motion becomes predictable. Therefore, the phrase "did not pass through it, adjusted its path" is treated here not as a conclusion, but as a claim about whether the measured positions begin to diverge from a gravitational prediction in a sustained way beyond what improved fitting and uncertainty shrinkage would naturally produce. A small body entering the inner observing volume begins as a set of points on the sky. Each point is a right ascension and declination tied to a timestamp. The object's distance is not directly visible from a single point. Distance is inferred through parallax, through curvature in the track across multiple nights, and through how the object's motion responds to Earth's own motion. Early on, the data are often sparse, and the fitted orbit can have many solutions that fit nearly equally well. In that stage, what looks like an adjustment can be only the normal tightening of the orbit as ambiguity collapses. The outer solar system frame therefore begins by emphasizing the difference between a path changing in the real world and a path changing on paper. A real change requires a force. A paper change can occur when a model is under-constrained. Gravitational motion itself can create apparent surprises because gravity is not a single pull. The Sun pulls the planet's pull, and the geometry of the observer changes nightly. When a small body passes through the planetary region, even a distant approach to a planet can bend its trajectory. Jupiter is the most influential for many comets. Yet other planets can matter when the geometry is favorable. A gravitational deflection is not an adjustment made by the object. It is the object following the field it is in. When observers compute an orbit, they include these perturbations. If early fits use simplified models or short arcs that do not yet constrain planetary influences, while later fits can shift once full perturbations and more data are included. This is one of the most common reasons why early orbital elements change. The outer region therefore treats the solar system as a known environment. The object does not need to decide anything. It is carried. The practical work in this region is to define what a gravitational prediction means. A gravitational ephemeris is produced by integrating the object's motion forward from an initial state. The initial state includes position and velocity at a reference time. If the initial state is uncertain, the ephemeris is uncertain. For a new object, the uncertainty often stretches along the direction of motion, forming an elongated region of possible positions on future nights. As more astrometry arrives, the region shrinks. Observers often experience this as the predicted path shifting. Yet that shift is simply the best estimate moving within a larger uncertainty cloud. The region begins by placing that experience into clear language. It is normal for early predictions to move. It is not evidence of a force. Astrometry has its own outer constraints. The object's position is measured against a star catalog. The measurement can be biased by seeing by tracking and by background stars. If the object is faint, the centroid can be pulled by noise. If it is near a star, blending can shift the centroid. If it has a weak coma, the photocenter can shift away from the nucleus. Each of these can create systematic errors that look like a trajectory deviation when the orbit is fit. Therefore, in the outer frame, the reliability of claims about path adjustment depends on the quality and consistency of the astrometric data. Positions measured with different instruments and different reduction pipelines can have small offsets. If those offsets correlate with time, they can mimic a force. This is why orbit refinement includes outlier rejection and weighting. It is also why independent astrometry is valuable. If multiple observers using different setups measure the same residual pattern, the case for a physical deviation strengthens. The outer region also includes the observer's motion. Earth rotates and orbits the Sun. This creates parallax and perspective effects. A nearby object can show strong apparent motion due to Earth's rotation and orbit. A distant object shows less. As Earth moves, the line of sight changes, and the object's apparent position relative to stars changes in a way that depends on distance. Therefore, a sequence of measurements is always a combined effect of the object's motion and the observer's motion. Orbit fitting disentangles these by using time and geometry. Yet early on, limited data can allow alternative distances that produce similar sky tracks over short arcs. When additional nights are added, the distance becomes better constrained and the fitted trajectory can shift. Again, this looks like adjustment, but is only improved inference. In this wide dynamical context, the phrase adjusted its path becomes a specific test. Do residuals remain after the best gravitational model is applied with careful astrometric treatment? A residual is the difference between predicted and measured position at a given time. If residuals are random and consistent with estimated measurement errors, the gravitational model is sufficient. If residuals show a systematic drift, a consistent direction, or a pattern that grows with time, then something is missing. That missing element can be a true non-gravitational force, or it can be a systematic bias in the data. The outer region does not decide between these yet. It sets the framework. It emphasizes that a real adjustment implies a real force, and that the first responsibility is to ensure that the gravitational baseline and the measurement chain are sound. The wide frame also recognizes that even a true deviation can be small. Non-gravitational accelerations in comets are usually tiny compared to solar gravity, but they accumulate. Over days and weeks, the accumulated displacement can become measurable. Whether it becomes measurable depends on the precision of the astrometry and on the time baseline. Therefore, a key date or window in which the object is bright and well placed can matter because it allows higher precision positions. Yet this still belongs to later regions. In the outer frame, the only claim that can be made is that if an adjustment exists, it should reveal itself as a persistent mismatch between gravity-only predictions and measured positions, after accounting for the normal evolution of uncertainty, and after accounting for known measurement biases. This region therefore ends with a calm statement of what is needed before any stronger language is justified. The orbit must be refined with adequate data coverage. The gravitational model must include planetary perturbations. The astrometry must be consistent and well calibrated. The residuals must be examined for structure. Only then is it meaningful to speak about path adjustment. The inquiry can then move inward to discovery track and early fits, not to repeat the story of detection, but to show how early provisional paths can shift and how to distinguish those shifts from a genuine physical deviation. The next step inward remains in the outer observational domain because the first task is still to secure the track before interpreting it as a sign of thrust or other forces. From the broad gravitational frame, the next region narrows to discovery track and early fits, because this is where the impression of an adjusting path often begins. A new object is first seen as a candidate, then confirmed as a moving body, then assigned an orbit that evolves as additional data arrives. In this region, the focus stays on process rather than on interpretation. The key is to describe how early orbit solutions behave when the observation arc is short, and how the normal tightening of uncertainty can resemble a change in the object's trajectory, even when the object is doing nothing more than following gravity. A survey image produces a detection at a particular time and sky position. A second image minutes or hours later may show the same point shifted. Software links these detections into a tracklet, a short segment of motion. Tracklets alone do not define an orbit. They define an apparent motion vector across the sky. With one night of tracklets, there are many possible combinations of distance and true velocity that can produce the same apparent motion. The early orbit fitting problem is therefore under-constrained. The solver chooses a best fit among many candidates, often using assumptions and priors to keep solutions physically plausible. This best fit can be good enough to predict the object's location the next night within a search region. That prediction is the practical purpose of early fits. It is not yet a refined physical description. When the object is recovered on a second night, the orbit fit improves dramatically because the time baseline grows and the curvature of the motion becomes more informative. Even then, a two-night arc can still allow alternative solutions. The fit can shift as a result of a small change in one measured position, especially if the target is faint and astrometric uncertainties are larger. This is why early ephemerides can move. The predicted position for a future night can shift by arc minutes or more as new data is incorporated. Observers experience this as the object altering course, but in reality, the observer's knowledge is altering. The region therefore distinguishes between the object's continuous path and the discontinuous updates of the fitted model. The biggest early source of apparent path adjustment is the collapse of distance ambiguity. A faint moving object could be relatively small and nearby or larger and farther. The orbit fit assigns a distance that best matches the early track. If later data indicates a different distance, the inferred velocity changes and the path changes. This change is not a force acting on the object. It is an updated solution in a higher dimensional parameter space. The outer region uses a simple principle. A real force would produce a gradual deviation from a stable model, while a distance ambiguity collapse can produce a sudden shift in predicted future positions as the fit jumps from one valley of solutions to another. Another early source is catalog and reduction differences. Different surveys use different star catalogs, different distortion models, and different centroiding algorithms. An object's measured position can differ by a small systematic offset between pipelines. If early data comes from one pipeline and later data from another, the combined set can show residual patterns that push the fit. Orbit solvers can handle this by weighting observations and by identifying systematic offsets, but early on, the system can appear unstable. This is why re-reduction of early images using consistent catalogs can improve stability. In this region, stability is a goal. The orbit should converge as the observation arc extends, and convergence is tested by whether solutions from different subsets of the data agree. Timing errors can also play a role in early fits. Astrometry depends on accurate timestamps because the object moves. A small timing error can translate into a positional error along the direction of motion. If a facility's timing is off by even a second for a fast-moving object, the position can shift measurably. Most professional systems handle timing well, but in heterogeneous data sets, small timing issues can occur. Therefore, early fits sometimes discard suspect data. This is not dramatic. It is the standard cleaning that makes later claims about subtle forces possible. The early phase can also be complicated by the object's appearance. If the object has a coma, centroiding can be biased. If the coma is symmetric, the photocenter can still coincide with the nucleus fairly well. If the coma is asymmetric, the photocenter can shift. Early detection images are often low resolution and low signal-to-noise, making it hard to assess coma. Therefore, early astrometry can include unseen photocenter bias. When later images at higher resolution reveal a coma and allow improved centroiding, the orbit fit can shift. Again, this looks like a path adjustment, but is a measurement refinement. The region emphasizes that this is one reason why claims of non-gravitational acceleration should not be made on the earliest data. The measurement regime is changing. During early fits, orbit uncertainty is often represented as a cloud of possible orbits. Each orbit in the cloud predicts a slightly different future path. As new observations arrive, the cloud shrinks. The central orbit moves slightly, and the uncertainty narrows. This is the expected behavior for a purely gravitational object. The region therefore defines a practical diagnostic if the orbit cloud continues to shrink, and the best fit remains within the shrinking cloud. In a smooth way, the system is behaving normally. If the best fit repeatedly shifts beyond what the previous uncertainty predicted, or if residuals remain structured even as the arc grows, then either the data have unaccounted systematics or the object is experiencing a real additional force. The phrase "did not pass through it" adjusted its path implies the second case, but the region holds that implication at arm's length. It does not accept it without the full pattern. The pattern required is persistence. A real acceleration would cause residuals to accumulate gradually and coherently. Early fit shifts caused by under-constrained distance or pipeline offsets can produce changes that are abrupt and inconsistent. Therefore, in this region, the object's behavior is assessed not by headlines, but by residual statistics and by how predictions compare to subsequent recoveries. If the object is repeatedly found near the predicted position and residuals remain noise like the impression of adjustment, is likely an impression of early uncertainty being resolved. If the object is consistently found offset from gravitational predictions in the same direction and with growing magnitude, then the case for a real deviation grows stronger. There is also a subtle psychological component in the early phase that affects how humans describe the same technical process. When an ephemeris changes, observers must change their pointing. They feel as if the object has moved unexpectedly because the target is not where the previous prediction said it would be. Yet the target is exactly where it must be on its true path. The prediction was the uncertain element. The region makes this explicit because it keeps the narrative calm. It replaces the sense of chase with the reality of refinement. By the end of this region, the early fit behavior is placed into a standard sequence. Discovery yields short arcs. Short arcs yield provisional paths. Provisional paths shift as distance and velocity become constrained. Pipeline differences and morphology can introduce early systematics. With more data, the orbit should converge. The convergence is tested by residual structure and by the stability of the solution under additional data. This prepares the next inward region, which focuses on how orbits are calculated in a more explicit way, because understanding the mechanics of orbit determination and uncertainty propagation is essential for distinguishing an adjusting path from a revised model. Only after that foundation is described can the narrative move inward to the specific sources of apparent path change, and then later to the physical forces that could produce a genuine deviation. With the behavior of early fits described, the next region explains how orbits are calculated in a way that stays accessible while remaining faithful to the underlying method. The purpose is not to teach mathematics in detail. It is to clarify which parts of an orbit solution are directly measured, which are inferred, and how uncertainty propagates through the process. This matters because the phrase "adjusted its path" can be rooted either in a true physical deviation or in a misunderstanding of how a best fit orbit evolves as more data arrives. In this region, the orbit is treated as a model that connects measurements, and the stability of that model is treated as evidence in itself. An orbit solution begins with astrometry times and sky positions. A sky position is a direction from the observer, not a distance. Therefore, an orbit solver must infer distance and velocity components that are not directly observed. It does this by using the fact that an object under gravity follows a specific class of trajectories. The solver searches for the trajectory that best reproduces all measured directions at their corresponding times. Because each measurement has error, the solver does not try to hit every point exactly. It tries to minimize the overall mismatch in a weighted sense, giving more influence to measurements that are expected to be more accurate. In practical terms, the orbit at a reference time can be expressed as a state vector position and velocity in 3 dimensions relative to the Sun. If that state vector were known exactly, the path could be integrated forward and backward by computing the gravitational acceleration from the Sun and planets at each moment. The integration produces predicted sky positions, as seen from Earth at the measurement times. The difference between predicted and observed positions is the residual. The solver adjusts the state vector to reduce those residuals. This adjustment is iterative. It begins with an initial guess and improves it step by step. The process continues until further adjustments no longer improve the fit meaningfully. Because the problem is nonlinear meaning. Small changes in the state vector can produce complex changes in predicted sky positions. The solver often uses linear approximations around the current best solution to decide how to adjust it. This is where uncertainty enters formally. The solver builds a covariance matrix, a compact representation of how uncertain the fitted parameters are and how they are correlated. Correlation matters because some combinations of parameters can change together while producing similar sky tracks, especially early in the observation arc. For example, a slightly larger distance combined with a slightly different velocity can fit the same positions over a short time span. This creates an elongated uncertainty region in parameter space. As new data arrives, the elongated region shrinks and rotates. The best fit moves within it. Uncertainty propagation from the orbit solution to future predictions is then straightforward in concept. If the state vector has uncertainty, future positions have uncertainty. The uncertainty in future sky position is often described as an error ellipse or a region on the sky. This region can be narrow in one direction and wide in another, reflecting the correlations in the state vector. For a newly discovered object, the region can grow rapidly with time into the future, because small errors in velocity accumulate into larger errors in position. This is why early recovery can be difficult. Yet once additional observations extend the arc, the uncertainty shrinks and the future prediction becomes tighter. A key feature of this process is that the best fit can change as new data is added, even if the object's true path has not changed. If early data leaves a broad uncertainty region, the best fit is one point in that region. As new data arrives, the region collapses toward the true state. The best fit moves accordingly. This movement can be larger than the formal uncertainty predicted by the early covariance if the early uncertainties were underestimated, or if early data had unrecognized systematics. Therefore, one of the diagnostics of orbit reliability is whether residuals are consistent with the estimated errors. If residuals are larger than expected, the covariance may be too optimistic. In that case, future predictions may shift more than expected when new data arrives. This is again a model behavior, not a physical path adjustment. Orbit calculation also depends on the force model. The simplest force model includes only the Sun's gravity. A more complete model includes the gravitational pull of the planets, and sometimes includes the Moon-large asteroids and relativistic corrections near the Sun. For many objects, Sun plus planets is sufficient. If the object passes close to a planet, or if the measurement precision is high, small additional terms can matter. If the force model is incomplete, residuals can appear. An early orbit fit might use a simplified model for speed, and later refinements might use a more complete model. This can shift the orbit solution slightly. Such a shift can be misread as the object changing its path. In reality, the model is changing. Time standards also matter. Precise orbit calculation depends on consistent timestamps. Observations are time-tagged in a standard timescale. The solver uses these times to compute the positions of Earth and planets at those moments. If time tags are inconsistent, or if a small timing bias exists in some observations, residuals can appear that have a coherent pattern. In high-precision cases, even small timing errors can matter. Therefore, orbit calculation includes data vetting not only to remove obvious outliers, but to ensure consistency in time and reference frame. The reference frame for sky positions matters too. Observations use star catalogs to translate pixel positions into sky coordinates. Modern catalogs provide extremely accurate star positions and proper motions. Yet if a reduction uses an older catalog or applies a distortion model imperfectly, systematic offsets can remain. These offsets can be small but coherent. In orbit fitting, coherent offsets can masquerade as a dynamical effect. Therefore, one of the strongest ways to stabilize an orbit is to re-reduce observations with a uniform catalog and distortion model. The region emphasizes this because it is a common step in moving from early provisional orbits to later refined ones. When an object is active, orbit calculation faces an additional challenge. The measured position may be the photocenter, not the nucleus center. The photocenter depends on coma brightness distribution. If the coma is asymmetric, the photocenter shifts. If the asymmetry changes with time, the shift changes. In orbit calculation, this introduces a time-dependent systematic error that can create residual patterns. A solver might interpret such patterns as a need for non-gravitational acceleration terms. Therefore, when activity is possible, orbit calculation and morphological assessment must be linked. In some cases, observers attempt to correct astrometry by modeling the coma and estimating the nucleus position. In other cases, they restrict orbit fitting to measurements taken when the object appears point-like or to high-resolution data. The region does not assume that such correction is always possible. It describes it as a consideration that influences how confidently one can claim a true path adjustment. In this region, the phrase "adjusted its path" becomes a statement about the force model and the residual pattern. If the gravitational plus planetary model fits the data with residuals consistent with measurement errors, then the orbit calculation has succeeded, and no extra force is required. If residuals remain structured and persist across data sets and reductions, then the force model may be missing something. The missing term could be a non-gravitational acceleration, but it could also be an unmodeled systematic in the data. The key is that orbit calculation provides the diagnostic language to separate these, the size, direction, and time dependence of residuals. By the end of this region, the process of orbit calculation is framed as a loop. Measurements are made with uncertainty. A model predicts those measurements. Residuals measure mismatch. The model is adjusted. Uncertainty is propagated. The model is tested against new data. Apparent path changes are often the visible symptom of this loop as it converges. A true physical path adjustment would appear as a mismatch that cannot be removed by improving measurement handling or by completing the gravitational model. This prepares the next inward region, which examines the specific sources of apparent path change in more detail because those sources are the most common alternative to a true non-gravitational force. Only after those alternatives are described can the narrative cross inward into the physical realm of non-gravitational forces as real causes rather than as placeholders for imperfect fitting. With orbit calculation clarified as a model fitting loop, the next region focuses on the sources of apparent path change, because these are the mechanisms that can make a trajectory seem to adjust even when no extra force is acting. This region stays in the outer observational domain. It treats the object's path as a product of inference and places special attention on how inference changes when new data, new reductions, or new assumptions enter. The claim that 3I Atlas did not pass through it, adjusted its path, can only become physically meaningful after these apparent sources are considered and found insufficient. The first source is simple uncertainty shrinkage. Early in discovery, a small change in one observation can move the best fit orbit noticeably, because the orbit is not yet tightly constrained. When later observations arrive, the range of allowed orbits collapses. The best fit can jump from one local solution to another that fits the growing data set better. This jump can look like a sudden change in the predicted path, especially if observers compare ephemerides from different days. In reality, the object's true path is continuous, and the jump is the model catching up. The diagnostic here is whether the earlier uncertainty region included the later best solution. If it did, the change is within expected uncertainty evolution. If it did not, then either the early uncertainties were underestimated or early data had systematics. The second source is data weighting and outlier handling. Orbit fitting depends on assumed uncertainties for each measurement. If uncertainties are too small for a subset of data, those points dominate the fit. If they contain systematic bias, the fit is pulled away from the true path. When later analysts change the weights or remove outliers, the orbit can shift. This shift can be large, even though the underlying data points have not changed, because the balance between them has changed. Outliers can occur for many reasons, blending with a background star, a cosmic ray affecting centroiding, poor seeing, or timing errors. In a moving object context, a single blended measurement can shift the centroid by a significant amount, especially when the object is faint. Therefore, a shift in the orbit after outlier removal is often a sign of healthier fitting, not a sign that the object changed course. The third source is star catalog and distortion model differences. Astrometry is only as good as the mapping from pixel coordinates to sky coordinates. If one set of measurements uses a catalog with small systematic errors or a distortion model that is slightly wrong, the positions can be biased in a direction that depends on where the object sits in the field. A moving object samples different field positions over time. The bias can therefore change with time in a coherent way. When later reductions use a more accurate catalog and a better distortion correction, the positions shift slightly and the orbit shifts with them. This can create the impression that the object's path has been adjusted. The diagnostic is whether the residuals shrink and become more random after re-reduction. If they do, the change is likely a correction of measurement bias. The fourth source is time stamping and time system handling. Most professional observatories use accurate clocks, but heterogeneous data sets can include small timing discrepancies. For a moving object, a small timing error translates into an along-track positional error. If the object moves quickly, even a fraction of a second can matter for high precision. If timing biases occur in one observatory's data, and that observatory contributes many points, the orbit can be pulled. Later, when those points are corrected or down-weighted, the orbit shifts. The diagnostic is whether the residuals for that observatory show a consistent along-track offset. If they do, timing or centroiding bias is plausible. The fifth source is the observer geometry changing in a way that exposes degeneracies. A short observation arc may not strongly constrain certain orbital parameters. As Earth moves along its orbit, the perspective changes and breaks degeneracies. The same object can then be seen from a different angle, revealing curvature that was previously ambiguous. When that happens, the orbit solution can shift. This shift can be pronounced, even if the new measurements are as accurate as the old ones. The shift is driven by geometry, not by force. This is particularly relevant for distant objects where parallax is small and early constraints on distance are weak. The diagnostic is that as the arc lengthens, the orbit should converge, and the predicted future positions should become more stable. The sixth source is gravitational perturbations that were not fully included or not well constrained early on. If a preliminary orbit did not account for planetary perturbations accurately, or if the orbit's uncertainty made the timing of planetary influences uncertain, later fits can shift once the object's proximity to planets and the timing of its passage are better constrained. This is still gravitational. It is not the object choosing to adjust. It is the model more accurately representing the gravitational environment. The diagnostic is that once a full n-body model is applied, residuals should shrink without the need for extra forces. The seventh source is photocenter bias from coma and asymmetric light distribution. This source is particularly dangerous because it can mimic the signature of non-gravitational acceleration. If the object develops a faint coma, the measured position may drift away from the nucleus as the coma brightens or changes shape. If the coma is sunward enhanced, the photocenter can shift toward the sun. If the coma is tailward enhanced, it can shift away. If the degree of asymmetry changes with time as the object warms or as viewing geometry changes, the photocenter shift becomes time-dependent. Orbit fitting can interpret this as a dynamical effect, yet it is an astrometric artifact. The diagnostic is whether the residual pattern correlates with seeing with image depth, with reported coma strength, or with the use of different centroiding methods. High-resolution observations that locate the nucleus more directly can also test this. If residuals disappear when using nucleus-centered astrometry, photocenter bias is implicated. The eighth source is processing choices in stacking and centroid measurement. Some observers measure astrometry on single frames. Others stack frames aligned on the object to increase signal to noise, then measure the centroid on the stacked image. Stacking can introduce small shifts if alignment is imperfect, or if the object's motion is not perfectly linear over the stacking interval. Stacking can also blend with faint background sources in a way that differs from single-frame measurements. These choices can create systematic differences. The diagnostic is whether astrometry derived from different methods shows consistent offsets. If so, the offsets must be understood before claiming a physical acceleration. The ninth source is misassociation, where detections from different nights are incorrectly linked to the same object. This is rarer in well-vetted data sets, but can occur when many faint objects are in the same region. A misassociation can produce an orbit that fits poorly and shifts dramatically as the association is corrected. This can create the strongest illusion of an object changing course, because the model may swing to accommodate inconsistent points. The diagnostic is the residual pattern and the ability to recover the object at predicted positions. A correct association produces consistent recoveries. An incorrect one produces failures. In this region, these sources are not listed to dilute the possibility of a real path adjustment. They are listed because each one is common enough that it must be ruled out explicitly, and because the object's claimed behavior can often be explained by one or more of them, especially early on. The practical method of ruling them out is convergence. A gravitational model with full perturbations and a consistent astrometric dataset should yield a stable orbit whose predictions are repeatedly confirmed. Residuals should become noise-like. If the orbit continues to require revision beyond what uncertainty evolution predicts, and if residuals remain structured across independent datasets and reductions, then the apparent path change may be more than an artifact. This sets up the next inward region, which focuses on gravitational influences only in a more coherent physical sense, emphasizing that many genuine changes in trajectory are still gravitational and do not imply any additional force. Before the narrative crosses into non-gravitational forces as a cause, it must give gravity its full explanatory power in the specific context of 3I Atlas, including how planetary perturbations and the Sun's field alone can produce trajectories that appear to bend and shift. Only after gravity's full role is described and the apparent sources are considered can the argument cross the boundary inward to residuals that persist beyond those explanations. With the sources of apparent path change laid out, the next region gives gravity its full explanatory role because many true changes in a trajectory are still gravitational and can be mistaken for an active adjustment if the language is not careful. In this region, the object is treated as passive in the sense that it follows the gravitational field. The field itself is not simple. It includes the Sun as the dominant mass and the planets as moving perturbing masses. When observers say an object's path bends in most cases, they are describing this field. The phrase "did not pass through it," adjusted its path can only become a statement about extra forces after this gravitational picture is complete. The gravitational path of a small body is determined first by its energy and angular momentum relative to the Sun. If the object is bound, its energy is negative and it follows an elliptical trajectory. If it is unbound, its energy is positive and it follows a hyperbolic trajectory. In either case, the trajectory is a smooth curve in space. The curve is not a straight line even far from the Sun, because the Sun's gravity extends indefinitely. A hyperbolic path has an incoming asymptote and an outgoing asymptote, and the angle between them is set by the object's speed and its closest approach, distance to the Sun. A faster object is deflected less. A slower object is deflected more. This is purely gravitational. Therefore, an object that approaches and then departs does not pass through on a straight line. It is bent by the Sun. The amount of bending is predictable once the orbit is known. Planetary perturbations add further bending. The planets orbit the Sun and carry their own gravitational fields. When a small body passes near a planet, the planet's gravity can change the small body's heliocentric energy and direction. This is the mechanism behind gravitational assists used for spacecraft. For small bodies, the effect can be subtle or strong depending on the distance of closest approach and the relative geometry. Jupiter is especially influential because of its mass. A small body that passes within a few Jupiter distances can have its orbit altered significantly, changing its future perihelion distance, or even ejecting it from the solar system. Even a more distant passage can create measurable perturbations in a precise orbit. Saturn can also matter, as can the inner planets, if the geometry brings the object close. These influences are not evidence of active behavior. They are gravity doing what gravity does. The observer's point of view can make gravitational curvature look like an adjustment. When an object is observed from Earth, the apparent track on the sky is the projection of its three-dimensional motion. This projection can change character as the object passes through different geometries. The track can curve more strongly at some times and less at others. The apparent speed can accelerate and decelerate due to perspective. For example, if the object's motion is partly toward or away from Earth, the sky motion can be slower, even though the object's true speed is high. As geometry shifts, sky motion can change. These changes can look like the object altering course in the sky, but they are the normal consequence of observing a three-dimensional trajectory from a moving platform. In this region, the key point is that an apparent bend in the sky track is expected even for a perfectly passive object. Gravitational perturbations can also be time-dependent in a way that complicates intuition. The planets move. The small body moves. The relative positions change continuously. Therefore, the net gravitational acceleration on the small body changes with time. The object is always being pulled not only toward the Sun, but also slightly toward the planets. Most of the time, the planetary pulls average out to small effects, but near conjunctions, when the object passes through regions where a planet's influence is stronger, the net acceleration can differ enough to matter for high-precision predictions. These effects are included in n-body integrations. If early orbit fits use simplified models, or if the object's distance and geometry relative to planets are not well known, early on predictions can change as those relations become clearer. This again is not a physical adjustment by the object. It is an improved representation of gravitational reality. One way to see gravity's full explanatory power is to consider how orbit solutions are extended backward and forward. If the orbit is integrated backward, it shows how the object approached the solar system. If the object had a close planetary encounter before discovery, the backward integration can show that the object's path was already altered by that encounter. Such a path can be surprising if one expects a simple inbound curve, yet it is still gravity. If the orbit is integrated forward, it shows how future encounters will alter the path. A body may appear to approach one way and leave another, not because it adjusted itself, but because the gravitational environment changed along the way. In some cases, the differences between inbound and outbound asymptotes can be strongly influenced by a planetary passage that occurs after perihelion. This is a standard feature of small body dynamics. In this region, the question becomes what should be called an adjustment. In strict physical language, any change in velocity is an acceleration, and any acceleration is a force. Gravity provides force. Therefore, gravity does adjust paths, but it does so in a predictable way for a given mass distribution. When the project title uses the phrase "adjusted its path," it suggests a deviation from the expected gravitational path, as if the object did something extra. This region therefore draws a calm distinction. A path that changes because of the Sun and planets is the baseline. A path that changes beyond that baseline is the special case. Observationally, the special case appears as residuals that remain after a full gravitational model is applied. Another subtle gravitational effect is the influence of small bodies, such as large asteroids, and of non-spherical mass distributions. For most cases, these are negligible. Yet for very precise orbit fits, and for trajectories that pass near large asteroids, small perturbations can be measurable. Similarly, relativistic corrections near the Sun can matter for extreme precision. In this region, these are acknowledged as part of a complete gravitational model when needed, but they are not treated as likely drivers of large apparent adjustments. Their main role is to remind that the gravitational baseline can be refined and that the baseline must be adequate before invoking any extra forces. The region also emphasizes that gravity-only motion produces smoothness. The gravitational field is continuous. The resulting trajectory is smooth. Apparent abrupt changes in predicted path usually come from model updates, not from gravitational physics. A real gravitational encounter can change heliocentric velocity significantly, but it still occurs through a smooth acceleration over the encounter time. Therefore, if the claim is that the path adjusted abruptly on a particular date, this is more likely a reflection of orbit refinement rather than a true sudden force event, unless that date corresponds to a close encounter and the geometry indicates such an encounter. For most objects, close encounters are not so tightly tied to a single date in observation language. They are events in the integrated trajectory. By the end of this region, gravity's role is complete and quiet. The Sun bends all inbound paths. Planets can further bend and reshape them. The observer's motion projects three-dimensional curvature into sky tracks that can look like changes in direction. A full gravitational model applied with accurate astrometry and proper weighting should capture these effects. Therefore, the threshold for claiming an extra adjustment is high. It requires persistent structured residuals that remain after the gravitational baseline has been applied and after the observational sources of apparent change have been addressed. This sets up the next inward region, which introduces residuals and mismatches as the first sign that gravity alone may be insufficient. That region does not yet commit to non-gravitational forces. It focuses on the statistical and geometric character of residuals and on what patterns in those residuals would justify crossing the boundary inward from gravitational description to physical cause. The inward path continues by noticing what does not fit calmly and precisely before naming why. With the gravitational baseline established, the next region focuses on residuals and mismatches, because this is where the claim of an adjusted path can first be expressed in a measurable form. A mismatch is not a feeling. It is the difference between what a model predicts and what a set of observations reports after the usual corrections and calibrations have been applied. In this region, the object is still treated as passive until the evidence forces a different stance. The task is to describe what residuals look like when gravity is sufficient, what they look like when something is missing, and how to distinguish a real, dynamical deviation from systematic measurement bias. This is the region where the narrative begins to lean inward toward cause, but it does so only through patterns in data. Residuals are computed for each observation as a small offset in the plane of the sky. They can be expressed as components along right ascension and declination, or as along track and cross-track components relative to the predicted motion direction. Along-track residuals measure whether the object is ahead of or behind its predicted position. Cross-track residuals measure whether it lies to one side of the predicted path. This decomposition matters because different physical and systematic effects produce different patterns. Timing errors tend to produce along-track offsets. Some astrometric distortions can produce position-dependent cross-track offsets. A genuine non-gravitational acceleration can produce both, but often in a structured, time-dependent way, tied to the orbit frame. In a well-behaving gravitational fit, residuals have three main properties. They are small compared to the estimated uncertainties. They are centered around zero with no persistent bias. And they do not show a trend with time. There can still be scatter because measurement noise varies with sky conditions and signal strength. There can be occasional outliers due to contamination. But the residuals look like noise rather than like a curve. When residuals look like a curve, it implies a consistent mismatch that accumulates. For example, if along-track residuals steadily increase with time, the object is being observed progressively ahead of prediction or progressively behind it. This is the signature of a small, unmodeled acceleration, or of a systematic drift in the time or centroiding. If cross-track residuals steadily increase, it suggests a consistent lateral mismatch, which can arise from an incorrect orbit plane orientation or from an unmodeled normal acceleration, but can also arise from consistent astrometric bias in a subset of observations. Residual analysis begins with a simple check. Do residuals correlate with observatory instrument or reduction pipeline? If one observatory's data show a consistent offset while others do not, the cause is likely systematic in that data set rather than physical in the object. If all observatories show the same trend, a physical deviation becomes more plausible. The same applies to seeing and brightness. If residuals grow when seeing worsens or when the object is fainter, then centroid bias and noise are implicated. If residuals persist even in the best seeing and highest signal data, the case for a real deviation strengthens. In this region, the emphasis is on separating data quality effects from physics. A key confounder, again, is photocenter bias. If the object has a faint coma that is asymmetric, the center of light can shift in a way that depends on the asymmetry. The asymmetry can depend on solar direction and on phase angle. Therefore, photocenter bias can produce residuals that mimic a force that is also linked to solar direction. This makes it dangerous because it can look like outgassing thrust. The diagnostic is multi-scale comparison. High-resolution astrometry or astrometry from images where the object is point-like should show smaller biases. If the residual trend is present only in data where the object appears extended or in data with coarse resolution, photocenter bias is likely. If the trend is present across high-resolution data as well, then a real acceleration is more likely. Another diagnostic is the stability of the residual pattern under changes in fitting choices. If a residual trend disappears when a few outliers are removed, or when weights are adjusted slightly, it may not be robust. A real acceleration should remain detectable under reasonable changes in weighting and data selection. A robust signal should also appear when the data are divided into subsets. For example, fitting an orbit to early data and predicting later positions should show a consistent offset in later data if an acceleration is present. Similarly, fitting to later data and predicting earlier positions should show a consistent mismatch in the opposite sense. This forward-backward consistency is important because it shows that the mismatch is not confined to one part of the data set. The temporal shape of residuals also matters. A non-gravitational acceleration, driven by solar heating, would often increase as the object approaches the Sun because outgassing tends to increase with heating. Therefore, residuals might be small early on and grow later. The growth could be nonlinear, reflecting the temperature dependence of sublimation. By contrast, a constant systematic bias in one observatory's astrometry would produce a more uniform offset, not an increasing trend. A timing bias would produce an along-track offset that might be constant or might vary if the object's apparent motion changes, but it would not necessarily track heliocentric distance. Therefore, plotting residuals against time and against heliocentric distance can help distinguish patterns. In this region, the emphasis is not on the exact model of outgassing, but on whether the residuals behave in a way that is naturally tied to solar distance, rather than to observational circumstances. There is also a geometric diagnostic in the orbit frame. A real outgassing thrust tends to have a direction relative to the Sun and the orbit. If a fit includes non-gravitational components, the best fit components can be compared across time intervals. If the direction is stable and the magnitude increases in a way that correlates with heating, it supports a physical interpretation. If the direction flips or changes unpredictably, it may indicate that the fit is absorbing noise or bias. Yet this diagnostic depends on sufficient data and on careful treatment of correlations between fitted parameters. In short arcs, the components can be poorly constrained and can change with small data changes. Therefore, the region remains cautious about over-interpreting component values until the arc is long and the data quality is high. Residuals are also influenced by the possibility of fragmentation. If the object breaks into multiple pieces, the measured position can jump if the brightness shifts between components, or if the photocenter moves. Fragmentation can also change the effective force from outgassing if new surfaces are exposed. In imaging, fragmentation can sometimes be seen as multiple condensations, but for faint objects it may not be visible. In residuals, fragmentation can appear as an abrupt change in residual pattern. Yet abrupt changes can also arise from changes in observing conditions or pipeline. Therefore, an abrupt residual shift is treated as a clue that demands cross-checks with imagery and with the timing of data sources. In this region, the phrase adjusted. Its path is translated into a specific question after applying the best gravitational model and after accounting for known systematics. Do residuals show a coherent, persistent pattern that indicates an extra acceleration? If the answer is no, the claim of adjustment becomes a description of orbit refinement and gravitational curvature, rather than of extra forces. If the answer is yes, the narrative is ready to cross the first boundary inward, moving from noticing what does not fit to asking what physical cause can produce the required extra force. By the end of this region, the residuals have been given a role that is both strict and quiet. They are the gate. They keep the narrative from leaping. They demand replication across observatories, independence from data quality confounders, stability under fitting choices, and a time dependence that makes physical sense. Only when those conditions are met does the inquiry move into the next region, which explicitly marks the transition from purely geometric fitting to physical interpretation. That transition is not a change in tone. It is a change in responsibility from describing the mismatch to identifying which kinds of forces can plausibly account for it without exaggeration, and without claiming more than the constrained evidence allows. With residual patterns established as the gate, the next region marks the first boundary inward, where the work shifts from describing mismatches to interpreting them physically. This boundary is crossed only if the residuals remain coherent after the gravitational baseline and observational confounders are addressed. The shift is subtle. The tone remains calm. The method remains constrained. What changes is the question. Instead of asking whether the orbit fit is stable, the inquiry asks what kind of force acting gently over time could produce the measured deviation without violating what is already known from brightness, morphology, and spectra. The phrase adjusted its path becomes here a matter of whether a small additional acceleration is required, and if required, whether it is consistent with known physical mechanisms for small bodies. A force that changes a trajectory must change velocity. In the solar system, aside from gravity, the most plausible sustained forces on a small body are those tied to radiation and mass loss. Radiation includes sunlight pressure and thermal re-emission, and mass loss includes outgassing and dust ejection. Collisions can also change velocity, but collision impulses are rare and typically abrupt, and they would often be accompanied by obvious changes in brightness or morphology if the collision were large enough to be dynamically measurable. Therefore, the boundary inward begins with sustained low-level forces as the primary candidates. The first candidate is outgassing thrust. When volatile substances turn to gas and escape the gas carries momentum. If the gas leaves symmetrically in all directions, the net momentum cancels and there is little or no net thrust. If the gas leaves more strongly from one region, the net momentum does not cancel. The object experiences a reaction force in the opposite direction. This is the same principle as a rocket, but in small bodies the effect is weak and distributed. The strength of the thrust depends on gas production rate, gas outflow speed, and the degree of asymmetry. It also depends on the object's mass. A small mass object can respond more noticeably to a given thrust. Therefore, when residuals suggest a non-gravitational acceleration, one immediate physical question is whether the required acceleration is consistent with plausible gas production and asymmetry, given the object's brightness and any spectral constraints. The second candidate is sunlight pressure acting on the nucleus. Sunlight carries momentum, and when it is absorbed or reflected, it exerts a force. For dust grains, this force is important because grains have large area relative to mass. For a typical nucleus-sized body, the area-to-mass ratio is small, so sunlight pressure is negligible compared to gravity. Yet if the body were extremely low density or unusually shaped in a way that increases area relative to mass, the effect could be less negligible. This regime is uncommon and demands strong evidence. In the boundary inward region, sunlight pressure is treated as a theoretical possibility that is generally disfavored unless the magnitude and direction of the inferred acceleration align with it, and unless other constraints imply an extreme area-to-mass ratio. The third candidate is thermal re-emission forces, sometimes called the Yarkovsky effect. An object absorbs sunlight and re-radiates heat. If re-radiation is not symmetric due to rotation and thermal lag, a small net force can occur. This effect is well established for asteroids, especially for smaller ones, and it can alter their orbits over long times. However, the effect is usually very small and typically measured over long arcs. For a newly observed object over a relatively short interval, it is less likely to be the dominant source of a measurable deviation unless the object is small and the astrometric precision and time baseline are high. In the context of a claim of immediate path adjustment, thermal forces are generally a slower background effect, yet they remain part of the physical map. The fourth candidate is dust mass loss without strong gas signatures. Dust ejection carries momentum too. If dust is ejected preferentially in one direction, it can produce a net force. In many cometary cases, dust is carried by gas, and dust thrust is part of the same phenomenon. Yet in some cases, mechanical shedding or fragmentation can release dust with limited gas. This can produce a visible dust coma and tail with weak gas lines and still provide some momentum exchange. The net effect depends on dust mass loss rate and ejection speed. Dust grains are heavier than gas molecules, so dust momentum can be significant if large amounts are ejected, but typical ejection speeds may be lower. Therefore, in this boundary region, dust is treated as a contributor that can either accompany gas thrust or, in special cases, provide thrust, even when gas lines are weak. Crossing the boundary inward also means linking force direction to observation geometry. A force tied to outgassing is usually correlated with solar illumination. Many active bodies vent more on the sunlit side. This tends to produce a net thrust that has a component away from the sun, or with some lag depending on thermal inertia. Therefore, an inferred acceleration that changes with heliocentric distance and that aligns in a physically plausible way relative to the sun is consistent with outgassing. A force tied to sunlight pressure would be directly away from the sun and would scale with inverse square of heliocentric distance. A thermal re-emission force would align with the direction of rotation and thermal lag and could be transverse. Therefore, the direction of residual drift in the sky and the fitted acceleration components in the orbit frame matter. They provide a way to test which force families are plausible. The boundary inward also insists on consistency with imaging and spectroscopy. If a strong non-gravitational acceleration is inferred, outgassing becomes plausible only if gas production could plausibly be present at the inferred level. If spectra detect gas emissions, the case strengthens. If spectra set strong upper limits on common gas tracers and images show no coma, then a large outgassing thrust becomes harder to reconcile unless the object is very low mass or releases species not traced by the observations. Conversely, if images show a coma and a tail and brightness rises beyond geometric expectations, then some mass loss is already indicated, and a modest non-gravitational acceleration becomes more plausible. The boundary region, therefore, does not treat orbit residuals as separate from the rest of the data. It treats them as one channel that must not contradict the others without explanation. A specific caution at this boundary is that the orbit solution can absorb small biases by creating a fitted acceleration that is not physical. If astrometric measurements are biased by a changing coma asymmetry, the solver may interpret this as a real acceleration. Therefore, before interpreting a fitted acceleration physically, the analysis must test whether the signal persists in data where coma bias is minimized. This can include restricting to high-resolution data using nucleus-centered astrometry methods, or comparing results across observatories with different pixel scales and seeing. If the acceleration disappears under these tests, the boundary inward is not crossed. The mismatch returns to the outer region of measurement bias. If the boundary is crossed, the claim adjusted, its path becomes a bounded statement. An extra acceleration of a certain magnitude and direction is required to match the data within uncertainties. This statement is still not an explanation. It is a requirement. The boundary inward region therefore ends with the recognition that the next step is to describe the general concept of non-gravitational forces in more detail, including how they are parameterized and how they are tested against data. That next region will remain general, staying within accessible language, while clarifying that non-gravitational does not mean mysterious. It means additional forces that are small and that arise naturally from the object interacting with sunlight and releasing material. The inward path continues by allowing for gentle pushes while holding each push against the measured constraints that have already been established. With the boundary inward crossed in principle, the next region develops the concept of non-gravitational forces in a way that keeps the language plain and the logic strict. Non-gravitational does not mean non-physical. It means forces other than the gravity of the sun and planets. In small body dynamics, these forces are usually small, and they often come from interactions with sunlight and from the loss of mass. The purpose of this region is to show how such forces are described and tested without turning them into a story. The phrase adjusted its path becomes here a statement about whether the data require one of these additional forces, and if required, how the force behaves with time and with distance from the sun. A non-gravitational acceleration is often described in components tied to the orbit. One component points radially away from the sun. One component points along the direction of motion. One component points perpendicular to the orbital plane. This choice is practical because solar heating and solar direction naturally define preferred directions, and because the orbit itself is the frame in which small changes accumulate into measurable deviations. A purely radial acceleration would push the object slightly outward or inward relative to the sun, and would change the timing and shape of the orbit in a characteristic way. A purely along-track acceleration would make the object arrive early or late compared to prediction, and would change the orbital energy slightly. A normal acceleration would tilt the orbital plane or shift the path out of the plane. Real cases often involve a combination. The next piece is how the magnitude varies. If outgassing drives the force, the magnitude depends on how much gas escapes and how that escape changes with heating. Heating depends on heliocentric distance, but the relation is not linear. Sublimation rates can rise sharply once a threshold temperature is crossed. Thermal inertia can create a lag between maximum sunlight and maximum outgassing. A dust mantle can delay response and then release suddenly. Therefore, in a general model, the non-gravitational acceleration is expected to be small at large distances and to increase as the object approaches the sun, possibly with a lag around perihelion. Some standard comet models use a fixed distance dependence designed to match typical water-ice sublimation behavior. This provides a smooth function of distance that rises toward the sun. However, if the object's activity is driven by more volatile substances, the rise could begin farther out. If activity is throttled by a mantle, the rise could be delayed. In this region, the important point is that the force should have a distance dependence that is physically plausible, and that testing this dependence against the data can provide clues without requiring direct sampling. Testing begins by fitting an orbit under gravity only and examining residuals. If residuals show a coherent pattern, a non-gravitational term is added and the fit is repeated. The key outcome is whether the residuals shrink and lose structure. If they do, the added term is improving the model. But improvement alone is not proof. A flexible model can always absorb noise. Therefore, the next test is robustness. Does the fitted non-gravitational term remain similar when data are divided into subsets such as early and late data? Does it remain when different observatories' data are used? Does it remain under reasonable changes to weighting? Does it remain when suspected coma-biased astrometry is excluded? A physically real acceleration should be present across these tests. A spurious acceleration should vary. Direction is also tested. If a fitted acceleration points in a direction that changes wildly between fits, it may be an artifact of correlations in the fit parameters. In short arcs, correlations can be strong. The solver can trade off small changes in initial velocity against small accelerations and achieve similar residual reductions. As the observation arc grows, these correlations weaken and the acceleration estimate becomes more stable if it is real. Therefore, in this region, claims about acceleration direction are treated as provisional until the data arc is sufficiently long and diverse. There is a special case where a non-gravitational acceleration can be inferred even without obvious coma or strong gas lines, when the object is very small or very low mass. The same thrust produces a larger acceleration if mass is small. In that case, modest outgassing could produce a measurable acceleration while producing minimal visible dust. This is physically plausible if the surface allows gas to escape without lifting much dust, or if the dominant gas species is hard to detect in the observed spectral range. Yet this plausibility depends on limits. If imaging sets strong limits on dust and spectroscopy sets strong limits on common gases, then the remaining plausible gas must be either a species not traced a low production rate, acting on a very small mass, or a highly collimated jet producing high thrust efficiency. Each of these carries uncertainty. In this region, the role of the non-gravitational model is to turn this into a bounded question. Given the measured acceleration and assumed outflow speeds, what mass would be required? Given the brightness and assumed reflectivity, what size would be required? Do those ranges overlap reasonably? If not, the interpretation must be reconsidered. Another special case is where radiation pressure or thermal forces become relevant. Radiation pressure depends on area and reflectivity. For dust grains, it dominates. For nuclei, it usually does not. If the inferred acceleration is directly away from the Sun and scales as inverse square of distance, that pattern could resemble radiation pressure. But for a nucleus to respond measurably, it would need an unusually high area to mass ratio. That implies either a very small object or an unusually low density. Thermal forces such as asymmetric re-radiation can produce a long track accelerations that accumulate over long periods, but they typically require knowledge of rotation state and thermal inertia, and are usually inferred over long time baselines. Therefore, in this region, these forces are held as alternative hypotheses that can be tested against the direction and distance dependence of the inferred acceleration, but they are not assumed. Non-gravitational forces also connect to the idea of an adjustment happening at a specific time. A physical force does not usually turn on instantly in a vacuum. It changes as conditions change. Yet certain physical thresholds can produce rapid transitions. A dust mantle can fail. A volatile pocket can be exposed. Amorphous ice can crystallize and release gas. If such a transition occurs, the acceleration could increase over a short interval. In residuals, this could look like a change in trend. Detecting such a change requires dense astrometry and careful data handling, because residual trends can also change when data sources change. In this region, the principle remains that a genuine physical transition should be supported by coincident changes in brightness morphology or spectra, if those channels are sensitive enough at the time. The region also emphasizes that non-gravitational modeling is not only about fitting, it is about prediction. Once an acceleration model is fitted, it predicts future positions. If the model is real, predictions should improve. If the model is spurious, predictions may not improve or may degrade. Therefore, the practical test is whether the object is recovered at predicted positions more reliably under the non-gravitational model than under gravity only. This test is powerful because it uses data not included in the fit. In this region, this predictive check is treated as one of the most important ways to keep interpretation honest. By the end of this region, non-gravitational forces are framed as gentle, testable additions to the gravitational model. They are described by direction and distance dependence, constrained by residual patterns, and tested by robustness and predictive success. The claim that 3I Atlas adjusted its path becomes a question of whether such an addition is required and stable. This prepares the next inward region, which focuses on outgassing as thrust more directly. Because among the non-gravitational candidates, outgassing is the one that most naturally ties back to the earlier regions of heating surface layers and possible coma and spectral signals. The inward path continues by connecting heat to motion, turning a fitted acceleration into a physical process that can be constrained without exaggeration. With non-gravitational forces defined as testable additions to gravity, the next region focuses on outgassing as thrust, because outgassing provides the most direct and widely observed mechanism by which small bodies alter their motion slightly. In this region, the object is treated as a physical system that can exchange momentum with escaping gas and entrained dust. The goal is to describe how the thrust arises, what it depends on, and how it can be constrained by the same measurements already discussed, including brightness trends, morphology, spectral detections, or limits, and the direction and timing of residual patterns. The phrase adjusted its path becomes here a question of whether the required thrust is compatible with plausible gas release, given what is seen and what is not seen. Outgassing begins when volatile substances near the surface or within a shallow layer reach temperatures where they can sublimate, meaning they turn from solid to gas without becoming liquid. The gas then migrates through pores and fractures and escapes to space. Each escaping molecule carries momentum. The sum of many molecules leaving in a preferred direction creates a net reaction force on the nucleus. The magnitude of that force depends on the mass flow rate of gas and on the average outflow speed. Outflow speed depends on temperature and on the molecular mass of the gas. It also depends on whether the gas expands freely from a surface or is funneled through a vent. In simple terms, warmer surfaces and lighter molecules tend to produce faster outflow, while vents can produce more collimated flow, increasing thrust efficiency in one direction. Asymmetry is essential. If the entire surface outgasses uniformly, the net force averages towards zero. Real surfaces are not uniform. Illumination is uneven. Some regions are insulated by dust mantles. Some are exposed. Some contain more volatile material. Some are shadowed. Rotation brings regions into sunlight and out of it. Thermal inertia can cause a lag, meaning the hottest region and strongest outgassing can occur after local noon. If the object's spin axis is tilted, seasonal effects can concentrate activity in one hemisphere. All these factors produce a pattern of gas release that is not perfectly symmetric. Therefore, a net thrust is plausible even without dramatic jets, but the net thrust depends on how those asymmetries integrate over rotation and over time. A narrow jet can produce strong net thrust, even with modest total gas production, while broad diffuse outgassing can produce little net thrust, even with high total production. The direction of the net thrust is constrained by physics and geometry. If activity is stronger on the sunlit side, the net thrust tends to push the object slightly away from the sun. However, thermal lag can shift the active region toward the afternoon side, adding a component along the direction of motion. This can increase or decrease orbital energy slightly. If activity is concentrated in a high-latitude region, a component out of the orbital plane can occur. These directional possibilities connect to the fitted non-gravitational acceleration components. If residual patterns suggest a primarily radial acceleration, it is consistent with sunlit side outgassing. If they suggest a significant transverse component, it may indicate thermal lag, a persistent jet geometry, or a particular spin state. In this region, such inferences are treated cautiously because the fitted components can be correlated and because coma bias can mimic certain directions. Yet direction remains a key clue. Outgassing thrust also connects to observable activity in dust and gas. Gas escaping can drag dust grains. If dust is lifted, a coma and tail can form. The brightness can increase beyond geometric expectations. The color can change, often becoming redder with increasing dust contribution. If gas is abundant, spectral emission features can appear. Yet these connections are not guaranteed. A surface can allow gas to escape through pores without lifting much dust if cohesion is strong. A dominant gas species can have weak emissions in the observed bands. Dust can be dominated by large grains that are less reflective per mass and therefore produce a weaker coma for the same mass loss. Therefore, in this region, the absence of a visible coma does not eliminate outgassing, but it constrains the dust coupling regime. Similarly, the absence of detected gas lines does not eliminate outgassing, but it constrains either the species mix the production rate or the observing sensitivity. The most direct dynamical constraint on outgassing is the relationship between thrust and acceleration. The acceleration equals thrust divided by mass. If an acceleration is inferred from orbit residuals, and if an outflow speed is assumed, then the required mass flow rate times asymmetry efficiency can be estimated for a given mass. If the mass is unknown, this becomes a family of solutions. The mass can be linked to size and size can be linked to brightness, but brightness depends on reflectivity, which can vary widely. Therefore, the region emphasizes that the resulting constraint is not a single number. It is a consistency check. For plausible ranges of size and reflectivity, does the required gas production fall within ranges that are consistent with spectral detections or upper limits? If spectroscopy detects certain species and gives a production rate, is that rate sufficient to account for the acceleration under reasonable thrust efficiency? If it is far too low, either the mass must be lower, the thrust efficiency must be higher, or the dominant gas is not detected. If it is far too high, the acceleration may be overestimated or contaminated by astrometric bias. Timing provides another constraint. Outgassing-driven acceleration should vary with heliocentric distance and with illumination. As the object approaches, the sun gas production tends to increase. Therefore, acceleration should become more detectable closer in. If residual patterns indicate a deviation beginning or strengthening around a specific interval, this can be compared to the time when the object crosses plausible activation thresholds for different volatiles, and to the time when brightness or morphology changes. A coherent alignment between these channels strengthens a physical interpretation. A mismatch weakens it. For example, an acceleration that appears to strengthen while brightness remains purely geometric and no coma is seen would be unusual and would require careful re-examination of astrometry biases and alternative force mechanisms. Outgassing also leaves signatures in the shape of the coma when it is present. A localized jet can produce a fan or a narrow feature. If the jet rotates with the nucleus, the feature can sweep and create spiral patterns in high-resolution images. On most distant faint objects, such fine structure is not resolved, but a symmetry near the nucleus can still hint at localized sources. If a persistent asymmetry aligns with the inferred acceleration direction, it supports the idea that the net thrust arises from that asymmetry. Yet this is a delicate inference, because morphology is shaped by dust dynamics and viewing geometry as well. Therefore, in this region, morphology is used as supportive context rather than as proof of thrust direction. The region also considers the possibility of episodic outgassing. Outbursts can release gas and dust, rapidly producing sudden brightness increases and expanding shells. Such events can also produce transient accelerations. However, a single short event is less effective at changing the orbit than a sustained force, unless the event is extremely large. Most orbit deviations attributed to non-gravitational effects are driven by sustained or repeated activity over weeks or months. Therefore, an outburst can explain abrupt photometric changes, but may not explain a smooth residual drift unless activity continues at some level afterward. In this region, the timing and persistence of residual patterns are used to distinguish sustained thrust from isolated events. When the project title suggests that the object adjusted its path rather than merely being bent by gravity, the outgassing thrust framework provides a measured interpretation. The object can adjust its path in the sense that it experiences a small net acceleration due to asymmetric mass loss. This is not agency, it is physics. The degree of adjustment is constrained by the magnitude of residuals and the time over which they accumulate. The cause is constrained by whether the required thrust is compatible with observed or constrained activity. If the data support this compatibility, then the adjustment claim becomes a calm statement. The orbit is best fit by including a small non-gravitational acceleration, consistent with plausible outgassing. If the data do not support it, then the claim remains unproven, and the path changes remain attributable to orbit refinement and gravity. By the end of this region, outgassing thrust is described as a bridge between heating and motion. It is bounded by mass, size, reflectivity, gas production, thrust efficiency, and directionality. It is cross-checked against morphology and spectroscopy. This prepares the next inward region, which focuses on the timing of the adjustment more specifically, because time is the axis along which both physical activation and measurement sensitivity evolve. The next step inward will describe how an apparent adjustment can be localized to an interval in the observing record. How to test whether such localization is real, and how timing can constrain which physical triggers are plausible without going beyond the evidence. With non-gravitational forces defined as testable additions to gravity, the next region focuses on outgassing as thrust, because outgassing provides the most direct and widely observed mechanism by which small bodies alter their motion slightly. In this region, the object is treated as a physical system that can exchange momentum with escaping gas and entrained dust. The goal is to describe how the thrust arises, what it depends on, and how it can be constrained by the same measurements already discussed, including brightness trends, morphology, spectral detections, or limits and the direction and timing of residual patterns. The phrase "adjusted its path" becomes here a question of whether the required thrust is compatible with plausible gas release given what is seen and what is not seen. Outgassing begins when volatile substances near the surface or within a shallow layer reach temperatures where they can sublimate, meaning they turn from solid to gas without becoming liquid. The gas then migrates through pores and fractures and escapes to space. Each escaping molecule carries momentum. The sum of many molecules leaving in a preferred direction creates a net reaction force on the nucleus. The magnitude of that force depends on the mass flow rate of gas and on the average outflow speed. Outflow speed depends on temperature and on the molecular mass of the gas. It also depends on whether the gas expands freely from a surface or is funneled through a vent. In simple terms, warmer surfaces and lighter molecules tend to produce faster outflow, while vents can produce more collimated flow, increasing thrust efficiency in one direction. Asymmetry is essential. If the entire surface outgasses uniformly, the net force averages towards zero. Real surfaces are not uniform. Illumination is uneven. Some regions are insulated by dust mantles. Some are exposed. Some contain more volatile material. Some are shadowed. Rotation brings regions into sunlight and out of it. Thermal inertia can cause a lag, meaning the hottest region and strongest outgassing can occur after local noon. If the object's spin axis is tilted, seasonal effects can concentrate activity in one hemisphere. All these factors produce a pattern of gas release that is not perfectly symmetric. Therefore, a net thrust is plausible even without dramatic jets. But the net thrust depends on how those asymmetries integrate over rotation and over time. A narrow jet can produce strong net thrust even with modest total gas production, while broad, diffuse outgassing can produce little net thrust even with high total production. The direction of the net thrust is constrained by physics and geometry. If activity is stronger on the sunlit side, the net thrust tends to push the object slightly away from the sun. However, thermal lag can shift the active region toward the afternoon side, adding a component along the direction of motion. This can increase or decrease orbital energy slightly. If activity is concentrated in a high-latitude region, a component out of the orbital plane can occur. These directional possibilities connect to the fitted non-gravitational acceleration components. If residual patterns suggest a primarily radial acceleration, it is consistent with sunlit side outgassing. If they suggest a significant transverse component, it may indicate thermal lag, a persistent jet geometry, or a particular spin state. In this region, such inferences are treated cautiously because the fitted components can be correlated and because coma bias can mimic certain directions. Yet direction remains a key clue. Outgassing thrust also connects to observable activity in dust and gas. Gas escaping can drag dust grains. If dust is lifted, a coma and tail can form. The brightness can increase beyond geometric expectations. The color can change, often becoming redder with increasing dust contribution. If gas is abundant, spectral emission features can appear. Yet these connections are not guaranteed. A surface can allow gas to escape through pores without lifting much dust if cohesion is strong. A dominant gas species can have weak emissions in the observed bands. Dust can be dominated by large grains that are less reflective per mass, and therefore produce a weaker coma for the same mass loss. Therefore, in this region, the absence of a visible coma does not eliminate outgassing, but it constrains the dust coupling regime. Similarly, the absence of detected gas lines does not eliminate outgassing, but it constrains either the species mix the production rate or the observing sensitivity. The most direct dynamical constraint on outgassing is the relationship between thrust and acceleration. The acceleration equals thrust divided by mass. If an acceleration is inferred from orbit residuals, and if an outflow speed is assumed, then the required mass flow rate times asymmetry efficiency can be estimated for a given mass. If the mass is unknown, this becomes a family of solutions. The mass can be linked to size and size can be linked to brightness. But brightness depends on reflectivity, which can vary widely. Therefore, the region emphasizes that the resulting constraint is not a single number. It is a consistency check. For plausible ranges of size and reflectivity, does the required gas production fall within ranges that are consistent with spectral detections or upper limits? If spectroscopy detects certain species and gives a production rate, is that rate sufficient to account for the acceleration under reasonable thrust efficiency? If it is far too low, either the mass must be lower, the thrust efficiency must be higher, or the dominant gas is not detected. If it is far too high, the acceleration may be overestimated or contaminated by astrometric bias. Timing provides another constraint. Outgassing-driven acceleration should vary with heliocentric distance and with illumination. As the object approaches, the sun gas production tends to increase. Therefore, acceleration should become more detectable closer in. If residual patterns indicate a deviation beginning or strengthening around a specific interval, this can be compared to the time when the object crosses plausible activation thresholds for different volatiles, and to the time when brightness or morphology changes. A coherent alignment between these channels strengthens a physical interpretation. A mismatch weakens it. For example, an acceleration that appears to strengthen while brightness remains purely geometric and no coma is seen would be unusual, and would require careful re-examination of astrometry biases and alternative force mechanisms. Outgassing also leaves signatures in the shape of the coma when it is present. A localized jet can produce a fan or a narrow feature. If the jet rotates with the nucleus, the feature can sweep and create spiral patterns in high-resolution images. On most distant faint objects, such fine structure is not resolved, but a symmetry near the nucleus can still hint at localized sources. If a persistent asymmetry aligns with the inferred acceleration direction, it supports the idea that the net thrust arises from that asymmetry. Yet this is a delicate inference because morphology is shaped by dust dynamics and viewing geometry as well. Therefore, in this region, morphology is used as supportive context rather than as proof of thrust direction. The region also considers the possibility of episodic outgassing. Outbursts can release gas and dust, rapidly producing sudden brightness increases and expanding shells. Such events can also produce transient accelerations. However, a single short event is less effective at changing the orbit than a sustained force unless the event is extremely large. Most orbit deviations attributed to non-gravitational effects are driven by sustained or repeated activity over weeks or months. Therefore, an outburst can explain abrupt photometric changes, but may not explain a smooth residual drift unless activity continues at some level afterward. In this region, the timing and persistence of residual patterns are used to distinguish sustained thrust from isolated events. When the project title suggests that the object adjusted its path rather than merely being bent by gravity, the outgassing thrust framework provides a measured interpretation. The object can adjust its path in the sense that it experiences a small net acceleration due to asymmetric mass loss. This is not agency, it is physics. The degree of adjustment is constrained by the magnitude of residuals and the time over which they accumulate. The cause is constrained by whether the required thrust is compatible with observed or constrained activity. If the data support this compatibility, then the adjustment claim becomes a calm statement. The orbit is best fit by including a small non-gravitational acceleration consistent with plausible outgassing. If the data do not support it, then the claim remains unproven and the path changes remain attributable to orbit refinement and gravity. By the end of this region, outgassing thrust is described as a bridge between heating and motion. It is bounded by mass size reflectivity, gas production, thrust efficiency, and directionality. It is cross-checked against morphology and spectroscopy. This prepares the next inward region, which focuses on the timing of the adjustment more specifically, because time is the axis along which both physical activation and measurement sensitivity evolve. The next step inward will describe how an apparent adjustment can be localized to an interval in the observing record. How to test whether such localization is real, and how timing can constrain which physical triggers are plausible without going beyond the evidence. With timing used to localize when a deviation becomes detectable, the next region focuses on the direction of the shift, because direction is often the most discriminating clue between different causes. A path adjustment is not only a magnitude, it has a vector character. In orbit fitting, a small acceleration can point radially along the direction of motion or out of the orbital plane, and each direction implies different physical mechanisms and different vulnerabilities to observational bias. In this region, direction is treated as information rather than as interpretation. The goal is to show how direction is inferred from residual patterns and how it can be cross-checked against geometry and against known biases without assuming a cause before the direction itself is stable. Direction can be described in two related frames. One is the sky plane frame, where residuals are seen as offsets in right ascension and declination, or as a long track and cross-track relative to the predicted motion. The other is the orbit frame, where accelerations are described as radial transverse and normal relative to the orbit. The orbit frame is more physically meaningful because it is tied to the Sun and the trajectory, but it is inferred from sky plane data through the orbit solution. Therefore, direction inference begins with a careful reading of sky plane residuals and then maps inward toward orbit frame components as the data allow. A sustained along-track residual drift indicates that the object is consistently ahead of or behind the predicted position along its apparent motion. This suggests an error in the modeled speed along the orbit. In a physical acceleration interpretation, this aligns with a transverse component, meaning a force that adds or subtracts speed along the direction of motion. Such a force can arise from outgassing with thermal lag, where the strongest outgassing does not occur exactly on the subsolar point, but is shifted. It can also arise from some thermal re-emission effects. However, an along-track drift is also exactly what a timing bias produces. If observation timestamps are systematically early or late, positions shift along the motion direction. Therefore, in this region, an along-track pattern demands a strong check for timing consistency and for correlation with observatory. If the pattern is present across independent observatories with independent timing systems, it becomes less likely to be timing bias. A sustained cross-track drift indicates that the object is consistently to one side of the predicted track. This suggests an error in the modeled trajectory direction in the sky plane. In an orbit frame, it could correspond to a normal component that changes the orbital plane or to a mismatch in the orbital elements that define the plane. A normal acceleration could arise if outgassing is asymmetric in a way that produces thrust out of the plane, such as activity concentrated in a high-latitude region on a tilted spin axis. Yet cross-track patterns are also vulnerable to astrometric catalog biases and to field distortion errors that can be direction-dependent. They can also arise from photocenter shifts that are not aligned with the motion direction. Therefore, in this region, cross-track patterns are treated as potentially meaningful, but require strong evidence of independence from instrument coordinate axes and field position. Radial versus anti-solar direction provides another directional diagnostic. A force tied to sunlight pressure would point directly away from the sun. An outgassing thrust often has a component away from the sun if activity is stronger on the sunlit side, but the direction can be modified by lag and by jet geometry. Photocenter bias from a coma can also shift the measured position in an anti-solar direction if the coma is tailward enhanced, because the light distribution is pulled away from the sun. This is a critical point. A residual pattern that looks like an anti-solar acceleration could be either true thrust or a measurement bias due to an anti-solar coma. Therefore, direction analysis must be coupled to morphology. If images show a tailward enhancement, then a photocenter shift in that direction is expected. If residuals align with that direction, the acceleration inference is suspect unless nucleus-centered astrometry is used. The anti-solar direction on the sky changes with time as geometry changes. A physical force tied to the Sun should produce a direction in the orbit frame that remains consistent relative to the Sun even as the sky projection changes. Similarly, a coma tail direction should remain roughly aligned with the anti-solar direction or within the expected dust tail range as that direction changes. Therefore, in this region, one of the most powerful checks is whether the inferred direction behaves consistently under changing geometry. If residual offsets rotate on the sky in step with the changing anti-solar direction, it suggests a sun-linked cause. If they remain fixed in the detector coordinate system or fixed relative to a particular observatory's field orientation, it suggests an instrumental cause. If they remain fixed relative to the object's motion direction, it suggests a timing or a long-track bias. Thus, direction is not only an angle. It is how that angle evolves as geometry evolves. Direction also interacts with the object's rotation state. A localized jet produces thrust in a direction tied to the surface normal of the active region. As the object rotates, the jet direction in inertial space changes. Over one rotation, the net thrust may average out, or it may produce a preferred direction if the jet is active only when illuminated, and if the spin axis orientation creates a repeating pattern. The consequence is that the net thrust direction can be stable over days, even though the instantaneous direction varies. In a low-cadence dataset, this can appear as a smooth acceleration. The region acknowledges this because it explains how a stable acceleration can exist without requiring the object to have a fixed nozzle. Yet it also means that direction inference from orbit fitting is an averaged quantity, not a direct measurement of a jet orientation. Therefore, the region avoids attributing too much detail to the fitted direction. The magnitude of the direction components can also help discriminate causes. A purely radial acceleration with little transverse component could be consistent with sunlight pressure or with symmetric sunlit side-out gassing with little lag. A significant transverse component could indicate thermal lag or a jet geometry. A significant normal component would be unusual and would suggest a tilted spin axis and high latitude activity, or a systematic bias affecting the plane solution. In all cases, the plausibility depends on whether the required magnitude is consistent with known outgassing thrust levels and with the presence or absence of visible activity. A large acceleration with a large normal component would be especially demanding because producing out-of-plane thrust requires sustained asymmetry in a stable direction relative to the orbit plane. Direction inference also benefits from comparing solutions using different data types. If radar were available, it could provide line-of-sight velocity constraints, but for distant, faint objects, this is unlikely. More realistic is the use of photometry and morphology as indirect checks. If a dust tail is observed, its direction provides the anti-solar and orbital reference. If a coma is asymmetric, its direction suggests where the photocenter might be biased. If the inferred acceleration direction matches the coma asymmetry direction, that is a warning sign. If it does not match, and especially if the object appears point-like, then photocenter bias is less likely, and a physical acceleration is more plausible. By the end of this region, direction has been turned into a structured set of tests. The residual offsets are decomposed into a long track and cross track. Their correlation with observatory and data quality is examined. Their evolution is compared to changing anti-solar and motion directions. Morphology is used to assess photocenter bias. Orbit frame components are treated as averaged quantities. This structure allows the claim of adjustment to become more precise if a deviation is present. It points in a certain direction relative to the Sun and orbit with uncertainty, and that direction either aligns with plausible physical forces or aligns with known biases. This prepares the next inward region, which focuses on the limits of measurement, because direction analysis can still be undermined by subtle biases. The next step inward will not add new physics. It will refine the reliability of the inference by describing how astrometric bias, affects stacking choices and calibration errors, can create false direction signals, and how these are controlled. Only by tightening these measurement limits can the direction and therefore the physical interpretation remain steady enough to support a calm statement that the object's path is being altered by non-gravitational forces rather than by the measurement process itself. With direction framed as a discriminating clue, the next region focuses on the limits of measurement, because any claim of a path adjustment ultimately rests on the reliability of the positions that define the orbit. The orbit is only as real as the astrometry that supports it. In this region, the goal is to describe the principal ways measurements can mislead, especially for faint-moving objects that may have a coma, and to describe the controls that keep those misleadings from turning into a false acceleration. The tone remains slow and neutral. The emphasis is on careful limits, because it is within limits that the phrase adjusted its path can either be supported or softened back into a story of refinement. The first limit is signal to noise. A centroid is a computed center of light. When the object is faint, the light distribution is dominated by noise. Random noise can pull the centroid in different directions from frame to frame. Over many measurements, random noise averages down, but in short arcs, it can create residual scatter that appears structured by chance. Signal to noise also interacts with background structure. A faint galaxy or star behind the object can distort the light distribution. This can shift the centroid in a direction that depends on the relative brightness and separation of the contaminant. As the object moves, the contaminant changes. This can create time-dependent centroid shifts that are not physical. Therefore, in this region, a key measurement control is background screening, including checking for close background sources and masking them when extracting centroids. The second limit is trailing. If the telescope tracks the stars and the object moves, the object will trail during an exposure. A trailed object has an elongated profile. The centroid of an elongated profile can be biased if the trailing is not symmetric, or if the centroid algorithm assumes a symmetric point spread function. Even if the centroid is unbiased, the uncertainty increases. Trailing also interacts with timing. The centroid of a trail corresponds to the average position during the exposure, not the beginning or end. If the timestamp used is not the mid-exposure time, and a long track error is introduced. Therefore, one measurement control is to use short exposures to reduce trailing, and another is to ensure that timestamps correspond to mid-exposure times. Tracking on the object avoids trailing of the object, but trails the stars, which can complicate plate solving and star catalog matching. Both modes can work if handled carefully, but each introduces different biases that must be managed. The third limit is atmospheric seeing and differential refraction. Seeing broadens images. When seeing is poor, the object's profile is broader, and centroid in precision decreases. If the object has any extension, seeing can smear it and change apparent asymmetry. Differential refraction means that the atmosphere bends light by an amount that depends on wavelength and air mass. If observations use different filters, or if the object and reference stars have different colors, small positional shifts can arise. Modern reductions correct for refraction, but residuals can remain. These residuals can correlate with air mass, meaning they can change systematically as the object rises and sets. Therefore, in this region, one control is to include refraction corrections and to compare residuals against air mass to check for patterns. The fourth limit is field distortion and star catalog systematics. A wide-field camera can have optical distortion that varies across the field. If the distortion model is imperfect, positions are biased in a way that depends on where the object lies. As the object moves across the field or across nights, the bias changes. Similarly, star catalogs have small systematic errors, and their proper motions must be applied correctly to the epoch of observation. If proper motions are ignored or mishandled, star positions are off, and astrometry inherits that error. These issues can be subtle and can produce coherent residuals that mimic a small acceleration. Therefore, a central control is consistent re-reduction using the same modern catalog and well-tested distortion models and the use of reference stars distributed around the object to reduce local distortion bias. The fifth limit is stacking and measurement strategy. Some observers measure positions on single frames. Others stack frames to increase signal. Stacking requires aligning frames either on the stars or on the moving object. Aligning on the stars and stacking can smear the object. Aligning on the object and stacking smears the stars. Both can introduce centroid bias if not handled properly. When aligning on the object's motion must be known accurately. If the assumed motion is slightly off, the object can smear in the stack, shifting the centroid. When aligning on stars, the object's trail shape can be affected by changes in seeing between frames. Therefore, in this region, a preferred control is to measure astrometry on individual frames when possible, and to use stacking primarily for detection and morphology, rather than for primary astrometry unless the stacking method has been validated against single-frame results. The sixth limit is the special case of coma and photocenter bias. If the object has a coma, the light is not concentrated at a single point. If the coma is symmetric, the photocenter can still represent the nucleus reasonably. If the coma is asymmetric, the photocenter shifts. The shift can be small or large depending on coma brightness relative to the nucleus. It can also change with time as activity changes or as viewing geometry changes. A tailward enhancement can pull the photocenter away from the sun. A sunward fan can pull it toward the sun. Importantly, these are the same directions that physical thrust effects may point. Therefore, photocenter bias is the most dangerous measurement limit for claims of non-gravitational acceleration. Controls for coma bias exist, but are not perfect. One control is to use small apertures and fit the inner core, which is more nucleus-dominated. Another is to model the coma and subtract it using a point spread function, fit for the nucleus, plus an extended component for the coma. Another is to use high-resolution imaging, where the nucleus can be more directly isolated, at least statistically. Another is to compare astrometry derived from different methods and see whether residuals change. If a non-gravitational acceleration is inferred from photocenter-based astrometry, but disappears when nucleus-centered methods are used, the acceleration is likely spurious. If it remains, it becomes more plausible. In this region, the emphasis is on this method dependence, because it is the most practical way to separate a real dynamical effect from a shifting center of light. The seventh limit is selection effects in the data. When an object becomes brighter, more data arrives, but the data are not uniformly distributed in quality. Some points come from large telescopes with high precision. Others come from small telescopes at higher air mass. If the fitting process does not weight these appropriately, the orbit can be pulled by lower quality data. Similarly, if the object's brightness varies, centroiding precision varies, and the distribution of errors can be non-Gaussian. Therefore, data weighting and robust fitting techniques are controls that keep a few biased points from creating a false trend. The eighth limit is the interpretation of fit improvements. Adding a non-gravitational term can always reduce residuals because it adds flexibility. Therefore, the control is not only residual reduction, but predictive success and stability. A real acceleration should improve predictions for future observations not used in the fit. It should yield similar parameter values when fitting different subsets. It should not depend strongly on a small number of points. In this region, these controls are emphasized because they are the last defense against overfitting noise. By the end of this region, measurement limits are not presented as obstacles, but as the structure that makes reliable inference possible. The object's path is defined through fragile measurements. The fragility is managed through controls, careful timing, trailing management, refraction, correction, consistent catalogs, cautious stacking, coma, aware centroiding, appropriate weighting, and predictive testing. When these controls are applied, the remaining residual patterns are more likely to reflect real physics. When they are not, the residual patterns can be illusions. This sets up the next inward region, which focuses on consistency across observations, because even well-controlled measurements can still carry local biases. Consistency across independent data sets is the strongest confirmation that a direction and timing pattern is physical. The inward path therefore continues by requiring repetition and agreement, before moving deeper into what an adjustment would imply about the object's physical state. With measurement limits and controls made explicit, the next inward region focuses on consistency across observations, because consistency is the strongest practical filter between a real physical effect and a local bias. A single instrument can be wrong in a coherent way. A single night can be contaminated. A single reduction pipeline can carry a systematic offset. When multiple independent observers using different telescopes, different detectors, different reduction approaches, and often different sky conditions converge on the same residual pattern, the pattern becomes harder to dismiss as artifact. This region treats consistency as a method, not as a rhetorical claim. It asks what kinds of agreement matter most, how agreement is tested, and how partial disagreement is interpreted. without exaggeration. Consistency begins with redundancy. The object is observed by more than one facility, ideally at overlapping times. Overlap matters because it holds geometry constant while changing instrumentation. If two facilities observe the object within the same night and measure positions that agree within their uncertainties, it increases confidence that the astrometry is well calibrated. If they disagree systematically, it flags a possible local bias in one dataset. Such a bias can be due to field distortion, star catalog differences, centroiding methods, or coma effects. Overlap also matters for timing because it tests whether timing biases are present in one system. Therefore, in this region, the strongest form of consistency is simultaneous or near simultaneous agreement among independent observers. The next level is consistency across nights. A residual pattern that persists over many nights is more meaningful than a pattern that appears for one night. If a non-gravitational acceleration is real, its integrated effect should be visible as a sustained drift in residuals across time, not as a single-day anomaly. Therefore, consistency analysis looks for trends that survive changes in sky position, air mass, moon phase, and observing cadence. A trend that persists under these changing conditions suggests a physical cause, while a trend that appears only under specific conditions suggests a measurement bias. For example, if residual drift appears only when the object is observed at high air mass refraction, or seeing effects may be involved. If it appears only when the object passes through a dense star field, blending may be involved. If it appears only when a particular observatory contributes most data, that observatory's systematics may be involved. Therefore, in this region, consistency is tested not only by the presence of multiple datasets, but by the presence of multiple observing conditions. Consistency is also tested across measurement methods. Some observers measure astrometry using point spread function fitting. Others use centroiding in apertures. Some attempt nucleus-centered methods when a coma is present. Some measure on individual frames. Some use object-aligned stacks. If the inferred residual pattern depends strongly on the method, it may be a measurement artifact. If the pattern persists across methods, it becomes more plausible physically. This is especially important for coma bias. A physical acceleration should remain when astrometry is made as nucleus-centered as possible. A coma-induced photocenter shift should change when the method changes. Therefore, in this region, cross-method consistency is treated as one of the most powerful tests. The concept of consistency also applies to orbit solutions themselves. Fit the orbit using one subset of data and predict positions for another subset. If the prediction errors show the same systematic pattern across multiple independent subsets, it suggests a real missing force. If the pattern is present for one subset but not another, it suggests local bias. This can be done by fitting separate orbits to data from different observatories and comparing the resulting orbital elements and predicted ephemerides. If different observatories yield consistent orbits within uncertainties, the data are mutually compatible. If they yield divergent orbits, the data may have systematic differences. In this region, the point is that the orbit is not a single sacred solution. It is a product of data and assumptions. Consistency is tested by whether independent products agree. Consistency must also be separated from shared bias. Multiple observatories can share the same star catalog, They can share the same reduction software. They can share similar detectors. If a systematic error exists in the shared element, then agreement does not guarantee truth. Therefore, the strongest consistency comes from diversity. Different catalogs, different pipelines, and different optical systems reduce the chance of shared bias. Space-based observations, if available, provide a different environment because they avoid atmospheric seeing and refraction. High-resolution adaptive optics observations provide another. In practice, such diversity is not always available, but even within ground-based data, there's often enough variety to test whether a pattern is robust. Consistency also extends beyond astrometry. If a physical outgassing-driven acceleration is present, there may be supporting evidence in photometry morphology or spectra. The support does not need to be dramatic. It can be subtle. A slight brightening trend beyond geometry can be consistent with rising activity. A faint coma detected in deeper images can be consistent with mass loss. Weak gas lines detected intermittently can be consistent with low-level outgassing. Conversely, if an acceleration is inferred, but photometry remains purely geometric, images remain point-like in deep stacks, and spectra show strong limits on common gases, then the inference becomes harder to support. It may still be possible if the object is small and the outgassing species are not traced, but the burden of proof rises. Therefore, in this region, consistency is treated not only as agreement across astrometric data, but as coherence across observational channels. Partial inconsistency is handled carefully. It is common for some observatories to report slightly different residuals because their uncertainties differ. It is also common for a weak coma to be detected in some images and not in others depending on depth and seeing. Therefore, inconsistency does not automatically negate a physical effect. It can reflect different sensitivities. In this region, the method is to normalize differences by uncertainty and sensitivity. If one data set is deeper and detects a coma, while another is shallower and does not, that is not a contradiction. If one data set has smaller astrometric uncertainties and shows a trend, while another has larger uncertainties and appears noisy, that is not a contradiction. Contradiction arises when a high-precision data set indicates no deviation, while another high-precision data set indicates a strong deviation over the same interval and under similar conditions. In such cases, systematics are likely. Therefore, consistency analysis is a weighted comparison, not a simple vote. When the project title asserts that the object adjusted its path, this region provides the standard by which that assertion becomes responsibly grounded. The adjustment, if real, should be recoverable from multiple independent astrometric sources, stable under method, changes designed to reduce coma bias, and coherent with the timing and direction expectations for plausible physical forces. It should also improve prediction of future positions. The improvement should be demonstrable, not just a reduction of residuals in the fitted data. If these conditions are met, the claim becomes a calm statement about the data requiring a small, non-gravitational acceleration. If these conditions are not met, the claim should be softened to a statement about evolving orbit solutions and measurement uncertainties rather than a physical adjustment. By the end of this region, the narrative is prepared to move inward to what the adjustment would imply, but only in the form of constrained implications. Consistency has strengthened the foundation. It has narrowed the range of explanations that can survive. The next inward region will therefore describe what a real path adjustment implies about the object's physical state, focusing on mass-size activity regime and surface properties while remaining explicit about uncertainties. It will not interpret meaning. It will describe consequences. In the structure of the outer to inner path, this is a natural inward move from observing agreement to inferring the simplest physical conditions that could produce the observed agreement without stepping beyond the evidence boundaries that the method has set. With consistency across observations treated as the strongest foundation, the next inward region examines what a real adjustment would imply, because implication is the first place where the narrative can drift into excess if it is not kept bounded. In this region, implication means conditional consequence. If an extra acceleration is required by the data and is robust, then certain combinations of physical properties become more likely, and others become less likely. The region remains calm by stating these consequences as ranges and relationships rather than as declarations. The object's interior remains unknown. The evidence operates at a distance. Yet a measured acceleration combined with brightness and any activity indicators can still constrain the object's mass-scale activity regime and surface behavior. The central relationship is simple. Net thrust equals mass times acceleration. The acceleration may be inferred from orbit residuals. The mass is unknown. Therefore, the product of mass and acceleration sets the required net thrust. If acceleration is small, the required thrust is small for any mass. If acceleration is larger, the required thrust grows. The thrust from outgassing depends on gas mass flow rate and outflow speed, and on how collimated or asymmetric the flow is. If the flow is strongly collimated into a jet thrust, efficiency is higher. If flow is broadly distributed, thrust efficiency is lower. Therefore, for a given acceleration, a small mass object with a moderately efficient jet could be consistent with modest gas production. A large mass object would require larger gas production or higher efficiency. Brightness provides a loose handle on size. An object's brightness depends on its cross-sectional area and its reflectivity. Reflectivity can vary widely among small bodies. Therefore, a given brightness can correspond to a small bright object or a larger dark object. If a coma contributes, brightness can be dominated by dust rather than by nucleus area. Therefore, size inference from brightness is uncertain unless the object is point-like and unless thermal infrared measurements provide independent size constraints. Even without such measurements, brightness still sets limits. An object cannot be arbitrarily small if it is that bright, and it cannot be arbitrarily large if it remains point-like without a resolved disk. In this region, size remains a range. That size range translates into a mass range when combined with density assumptions. Density also varies. Cometary nuclei can have low bulk density due to porosity. Some rocky bodies have higher density. For an object where activity is possible, low density is plausible, but it cannot be assumed. Therefore, implications are expressed as compatibility checks across plausible size and density ranges. If a real acceleration is inferred, and is relatively large compared to typical cometary non-gravitational accelerations, one implication could be that the object is small or low mass. This does not require an extraordinary thrust. It requires a high acceleration for a modest thrust. If spectroscopy shows only weak gas emission and images show little dust, yet acceleration is inferred. The small mass implication becomes more relevant because a small mass allows weak outgassing to have a noticeable effect. In such a case, another implication is that the outgassing may be gas-rich and dust-poor, either because the surface is cohesive or because gas escapes through pores without lifting many grains. The surface layer model described earlier becomes relevant. A mantle can allow gas to leak while suppressing dust. The implication is not that the object is exotic. It is that its surface conditions place it in a regime where thrust can be present without obvious dust features. If a real acceleration is inferred, and images show a coma and a tail, the implication shifts. The object is losing mass in dust and likely in gas. The acceleration then provides a way to constrain the degree of asymmetry. If the coma appears symmetric but a strong acceleration is inferred, the symmetry would need to be deceptive, or the gas thrust would need to be collimated in a way not obvious in dust morphology. If the coma appears asymmetric with a clear sunward or tailward enhancement, and the acceleration direction aligns, then the implication is that the asymmetry is real and persistent enough to produce net thrust. This links morphology to dynamics. Yet the region remains cautious because coma asymmetry also biases astrometry. The implication is therefore conditional. If nucleus-centered astrometry confirms the acceleration, then the asymmetry can be interpreted as physical rather than purely as a measurement artifact. Direction also carries implications. A primarily radial acceleration suggests that sunlit side activity dominates with limited thermal lag. A significant transverse acceleration suggests thermal lag or a persistent jet geometry that produces net thrust along or against the direction of motion. A significant normal component suggests either a tilted spin axis and asymmetric high-latitude activity, or a measurement bias affecting the plane solution. If a normal component is robust across diverse datasets, the implication is that activity has a stable three-dimensional asymmetry. That would constrain the spin axis orientation relative to the orbit plane and would suggest that the active region does not average out over rotation. This is possible if the active region is near a pole, or if illumination geometry keeps it active preferentially. Again, this is an implication, not a claim of known spin state. Timing also implies something about thermal response. If the acceleration becomes detectable only after a certain distance or interval, and if this aligns with the appearance of activity indicators, the implication is that a threshold was crossed. That threshold could be activation of a particular volatile exposure of fresh material or failure of a mantle. A gradual increase implies gradual warming and increasing sublimation. A more abrupt increase implies a barrier change or a new source opening. If the acceleration appears without clear activity indicators, the implication might be that measurement sensitivity is the limiting factor, or that the activity is in a channel not easily observed, such as gas species with weak optical tracers. In this region, timing implication is always tied to detectability, because detectability changes as the object brightens and as observing cadence increases. If the adjustment is confirmed, another implication is the need for continued monitoring, because the acceleration can change. Non-gravitational forces in comets can vary strongly with time. As the object approaches, perihelion activity can rise. After perihelion, it can decline. Seasonal shifts can change which regions are illuminated. Outbursts can add transient changes. Therefore, a measured acceleration at one interval does not guarantee the same acceleration later. The implication is that orbit prediction requires continued updating and that the physical interpretation should track changes rather than assume constancy. This is an observational implication as much as a physical one. It suggests which kinds of data are most valuable. Dense astrometry, combined with deep imaging and periodic spectroscopy, especially around intervals where geometry and heating change rapidly. An implication that must be handled carefully is whether adjustment suggests something beyond known physical mechanisms. In this region, the disciplined approach is to avoid that leap. Outgassing, dust ejection, sunlight pressure on small fragments, and thermal forces are all known and can produce measurable deviations under certain conditions. A claim that none of these can apply would require a strong demonstration that measured acceleration, magnitude, and direction are incompatible with all plausible mass and activity regimes. That is a high bar and is not implied merely by surprise. Therefore, the innermost implication is conservative. If an adjustment is present, it indicates an additional force consistent with known small body physics unless and until constraints show otherwise. By the end of this region, implication is structured into a set of conditional consequences. Acceleration magnitude implies a relationship between thrust and mass. The visibility of dust and gas constrains which thrust mechanisms are plausible. Direction implies whether sun-linked, lag-linked, or plane-linked asymmetries dominate. Timing implies thresholds or gradual response. Variability implies the need for continued monitoring. This prepares the final inward region, which states what remains uncertain and which observations most efficiently reduce those uncertainties, concluding the 15-section arc. The final region will not add new speculation. It will inventory the constrained claims that can be made and the open parameters that remain, maintaining the same calm tone and avoiding meaning-making as the narrative approaches its final boundary. With implications stated as conditional consequences, the final region turns to what remains uncertain and what observations matter next, because the most responsible ending is an inventory of boundaries rather than a final verdict. The project title asserts that 3I Atlas did not pass through it, adjusted its path. After moving from the outer gravitational frame through orbit-fitting residuals measurement limits, cross-dataset consistency and physical implications, the title's claim can now be held in a constrained form. Either the data support a robust additional acceleration consistent with known mechanisms, or they do not. In both cases, the remaining uncertainties can be named precisely, and the next observations can be described as the most efficient way to narrow them. The first uncertainty is whether any inferred deviation is truly dynamical or partly astrometric. Even with careful controls, coma-induced photocenter bias remains difficult to eliminate completely if the object is faint and the coma is subtle. If the object is point-like in most images, this uncertainty shrinks. If the object is extended, the uncertainty grows. The most direct way to reduce it is to obtain high-resolution imaging that isolates the nucleus, or at minimum constrains the coma contribution in the inner pixels. If the nucleus position can be measured independently of the coma, then the orbit residuals become a cleaner probe of forces. If such imaging is not available, the uncertainty remains and must be carried alongside any acceleration claim. The second uncertainty is size and mass. Brightness alone cannot yield size without reflectivity, and reflectivity is rarely known a priori. If the object has a coma, brightness is not even dominated by nucleus area. Without a size estimate, mass remains unconstrained, and without mass, the thrust required for any acceleration remains ambiguous. Thermal infrared observations provide the most direct way to constrain size because they measure emitted heat, which depends on surface area and temperature. Combined with optical brightness, thermal data can also constrain reflectivity. Even a limited thermal detection can narrow size enough to make dynamical interpretations more concrete. If thermal data are not available, size and mass remain ranges, and the physical implications remain conditional. The third uncertainty is composition and volatile inventory. Spectroscopy can detect certain gas species and place limits on others, but no single spectral band covers all relevant volatiles. Ground-based observations are limited by atmospheric absorption in parts of the infrared. Optical spectra detect certain radicals that are indirect proxies for parent molecules. Therefore, a lack of detected lines does not prove lack of outgassing. It proves only that those specific features are below detection. To reduce this uncertainty, broader wavelength coverage is needed, including near-infrared access to key molecules when possible, and repeated observations to catch variability. If gas species are detected, production rates can be estimated and compared to any inferred acceleration. If not, upper limits still help, but ambiguity remains about untraced species. The fourth uncertainty is the dust regime. Imaging can detect a coma and tail, but turning that into a dust mass loss rate requires assumptions about grain sizes, velocities, and reflectance properties. Tail geometry can constrain size sorting in a qualitative way, but quantitative inference remains model-dependent. If a dust tail is present time series, imaging can reveal how features move, which constrains velocities. Polarimetry, where available, can constrain dust properties, but such measurements are challenging. Without these, dust remains a broad qualitative indicator. Yet even qualitative information matters, because it indicates whether the object is coupling gas to dust strongly or weakly, which in turn affects how thrust might manifest. The fifth uncertainty is rotation state and active region geometry. Non-gravitational acceleration depends not only on total outgassing, but on how outgassing is distributed on the surface and how it varies with rotation. A stable transverse or normal component implies a stable asymmetry that does not average out. Without knowledge of rotation period and spin axis orientation, that inference remains uncertain. Photometric monitoring can sometimes reveal rotation through periodic brightness variations, but coma can dilute this signal. High-cadence data can still detect periodicity if the nucleus contributes enough light, or if coma features repeat. If rotation can be measured, and if the spin axis can be constrained through modeling of jets or seasonal activity, then the direction and variability of the acceleration can be tied more directly to physical geometry. The sixth uncertainty is whether the apparent adjustment is sustained or transient. A non-gravitational acceleration inferred over one interval may not remain constant. Activity can rise and fall with distance. Mantle changes can open or seal vents. Outbursts can produce short-term effects. Therefore, continued astrometry across changing heliocentric distance is necessary to characterize the force's evolution. A sustained acceleration with a smooth distance dependence is easier to interpret physically and to model predictively. A variable acceleration demands a more cautious approach and is more sensitive to data heterogeneity and coma bias. Continued monitoring also improves the orbit, which reduces uncertainty and improves the ability to detect small deviations. These uncertainties define what remains open, and they also define the practical next steps that reduce the open space most efficiently. If the central claim is a path adjustment, the primary needed data remain high-quality astrometry with controlled coma bias collected by multiple independent observatories over a long enough arc to separate true acceleration from model correlations. Supporting data include deep imaging to characterize coma and tail presence, repeated photometry to test for rotation, and to track activity onset and evolution, and spectroscopy, with enough sensitivity and wavelength coverage to detect or constrain key gases. Thermal observations, when feasible, are especially valuable because they reduce size and mass uncertainty, making the dynamical and physical interpretations more concrete. If these observations converge, the title statement can be expressed in a restrained final form. The object's path is primarily governed by gravity, as all small bodies are. If residuals persist after full gravitational modeling and careful measurement controls, then a small additional acceleration is present, most plausibly arising from asymmetric mass loss, driven by solar heating, consistent with known small body behavior. If residuals do not persist under these controls, then the apparent adjustment is best understood as the normal evolution of orbit solutions under improving data and changing observing conditions, with gravity and measurement uncertainty accounting for the observed changes in predicted path. In either case, the end state is not a single dramatic conclusion. It is a set of constraints that either require an extra force or do not, and a set of measurements that tighten those constraints further as the object continues along its trajectory. The final region therefore closes by holding the claim at the level of evidence. The sky positions remain the foundation. The model remains the test. The residuals remain the gate. The physical mechanisms remain those that are known and that can be constrained by data. What remains uncertain is named, not filled. The path forward is a list of observations in concept, but in tone, it is simply a continuation of the same careful practice measure, compare, test, and allow only what persists to stand. The night settles into a quieter pace, and the object's claimed adjustment becomes a softer kind of certainty, the kind that lives inside error bars and repeated measurements. Positions arrive as small marks on a sky map, each one tied to a moment that cannot be repeated, each one carrying its own small blur of atmosphere optics and background. When many of these marks agree, the blur becomes narrower, and the orbit becomes less like a guess and more like a track that holds steady under new data. If an extra acceleration is present, it remains small enough that it is never seen directly. It is seen only as a persistent difference that refuses to disappear when the gravitational model is complete and when the measurements are handled with care. If it is not present, then what remains is the natural story of convergence, where predictions stop wandering and begin to stay in place, because the path was always there, and the model has finally caught up to it. In either case, the same calm practice continues. A residual is checked against the night's conditions. A drift is checked against the next night's positions. A direction is checked against geometry that changes slowly as Earth and the object both move. A faint hint of extension in an image is checked again in deeper frames, and then checked again in data from another site, until it is either a feature that persists or a feature that fades back into noise. A spectral line is treated the same way, asked to appear again at the right shifted wavelength, asked to survive different reductions, asked to remain when the sky background is handled differently. Nothing is forced into certainty, and nothing is discarded without reason. The record becomes a set of constraints that grow tighter as the object continues, and the constraints are enough. They describe a trajectory governed by gravity, and if the data require it, a gentle additional push that is still part of ordinary physics in sunlight and escaping material. The last minutes of attention return to the simplest view. A small body moves through a field of stars. The stars do not move. The body does. The measurements follow. The model follows. The claims narrow until only what is repeatable remains.